Hi, I'm Cole.
And I'm Grace. Welcome to the Deep Dive.
Welcome to the Deep Dive. We dig through the sources so you don't have to, giving you the essential insights.
Today, we're looking at the roots of something huge, artificial intelligence.
Mm.
It feels so modern, but its story goes way back.
Right, AI is everywhere now, from our phones to, well, science labs. But who actually got the ball rolling? Who laid those first critical stones?
That's a great question, and one name really stands out, John McCarthy. You could argue he's the one who not only named the field, but also built some of its earliest, most important tools.
Exactly. And that's our focus for this deep dive. We want to unpack McCarthy's massive contributions, like how he actually coined the term artificial intelligence.
Yeah, and his work on the Lisp programming language, which was foundational for AI for, gosh, decades.
Plus his fundamental ideas about AI research and how machines might reason. We've pulled this from great sources, the original Dartmouth proposal, Stanford archives, McCarthy's own papers.
So we're aiming for a really solid overview of a true AI pioneer.
Let's dive in. So the term itself, artificial intelligence, where did that actually come from?
Okay, so it wasn't just something he casually said. John McCarthy specifically coined it for a really important event, the 1956 Dartmouth Summer Research Project.
Dartmouth 56. That's often called the birthplace of AI as a field, isn't it?
That's the one. It's where it all formally began. And the name came from the proposal document for that summer project.
A specific document. Tell us about that.
Yep, it's titled Proposal for the Dartmouth Summer Research Project on Artificial Intelligence. It's dated August 31st, 1955.
Wow, 55.
Yeah, and McCarthy co-authored it with Marvin Minsky, Nathaniel Rochester, and Claude Shannon, other huge names, by the way. The original typescript was 17 pages plus a title page. You can still find copies at Dartmouth and Stanford.
So what was the big idea in this proposal? What was the core belief that launched this whole thing?
Well, it was incredibly ambitious for the time. The core conjecture was, and I'm quoting roughly here, that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it.
That's a bold statement. Basically saying intelligence isn't magic, it's programmable.
Pretty much. They were throwing down the gauntlet, saying, we can build intelligent machines if we figure out how intelligence works precisely enough.
Okay, so what were they actually hoping to achieve that summer? What were the goals?
They were aiming really high. The proposal talks about finding ways to make machines use language, form abstractions and concepts.
Like thinking?
Kinda, yeah. And solve problems usually reserved for humans, and even improve themselves. It's amazing how those goals from almost 70 years ago still drive AI research today.
It really is. But they must have known it wouldn't be easy. Did they see the obstacles?
Oh, definitely. And what's really insightful is they noted the main obstacle wasn't the computers themselves, the hardware capacity.
Which is what you might expect back then.
Right. Instead, they said it was, quote, our inability to write programs taking full advantage of what we have. It was a software problem, a programming problem. How do we instruct these machines to be intelligent?
That's incredibly prescient. So the proposal identified specific parts of this big AI problem. Let's maybe group some of those. They talked about programming computers to mimic human abilities.
Exactly. On one hand, just the basic idea that if a human can do a job, a computer could theoretically be programmed to do it. They saw the potential, even with those early machines.
If only they knew how to program it.
Right. And then specifically, how can a computer be programmed to use a language? This is fascinating. They guessed that human thought involves manipulating words based on rules of logic and, educated guesses. Language was key.
Which sounds very familiar in today's world of large language models.
Absolutely. It's like they saw it coming, in a way.
Okay, so beyond language, what other cognitive stuff were they looking at? Learning, thinking.
Yes. They discussed neuron nets, basically early ideas about arranging artificial neurons to form concepts, like precursors to today's neural networks.
Wow.
And abstractions. How can machines generalize from data? That's a core part of intelligence, right? Recognizing patterns, forming concepts, and also self-improvement. The idea that a truly smart machine would need to learn and get better on its own. Hints of machine learning way back then.
So learning, abstracting, what about the limits? Did they think about computation itself?
They did. Under the heading, Theory of the Size of a Calculation, McCarthy and Shannon were already working on this. It wasn't just if a machine could solve something, but how efficiently, how much time, how much memory.
Setting the stage for complexity theory.
Exactly. And finally, they touched on randomness and creativity. They speculated that maybe creativity isn't just logic, but it involves some kind of guided randomness or educated guesses.
Interesting. Like intuition, almost.
Maybe. That creativity needs a spark of unpredictability, but directed somehow. It's a really cool idea.
Okay, so that's the conceptual birth. Let's shift gears to a practical tool McCarthy created that really fueled early AI, Lisp.
Lisp, yes.
Yeah.
Stands for Lisp processor, designed by McCarthy in the late 1950s. And get this, it's the second oldest high-level language still in common use. Only Fortran is older.
Still in use. Why did he create it? What was the need?
He needed a language specifically for AI programming on the IBM 704 computer. He was inspired by some earlier languages, but wanted something more algebraic. Crucially, he wanted support for recursion.
Where a function calls itself.
Right, which is super powerful for breaking down complex problems. And he also wanted a modern if-then-else structure, which sounds basic now, but was pretty novel then.
So Lisp wasn't just for AI, it introduced fundamental programming concepts.
Oh, absolutely. Lisp was packed with innovations. Things like tree data structures, essential for representing complex relationships.
Okay.
Automatic storage management. McCarthy actually invented garbage collection around 1959, specifically for Lisp. It automatically cleans up memory the program isn't using anymore, a huge deal.
I bet. Managing memory manually is tough.
It is. Lisp also pioneered dynamic typing flexibility in how data types are handled. Conditionals, the if-then-else thing, higher-order functions, meaning functions can be treated like data, passed around, manipulated. Very powerful for abstraction.
Wow, quite a list.
And there's more. The first Lisp compiler was written in Lisp itself by Tim Hart and Mike Levin in 1962, a self-hosting compiler.
That's meta.
Totally. And it popularized the REPL, the read evil print loop, that interactive prompt where you type something that the computer does it and shows you the result immediately. Great for experimenting.
Lisp is also famous for its syntax, right? All those parentheses.
Yes, the S expressions are symbolic expressions. It uses this fully parenthesized prefix notation operator first, then the arguments, all wrapped in parentheses.
Looks a bit strange at first.
It can, but the magic is what it enables. Homogeneity. It's a fancy word meaning the code is the data. Lisp code is represented as Lisp lists.
Code is data. How does that help?
It means Lisp programs can easily manipulate other Lisp programs or even themselves. This allows for incredibly powerful macro systems. Programmers can essentially extend the language, tailor it to their specific AI problem.
So you could teach the language new tricks, essentially.
Exactly. That flexibility was perfect for AI research, where problems were often ill-defined and required novel approaches. It just accelerated everything.
So Lisp became the go-to language for AI.
Pretty much immediately after it was published around 1960. Yes, for decades, if you were doing serious AI, chances are you were using Lisp or one of its dialects.
Okay, so McCarthy coined the term, built the language. What about his direct contributions to AI ideas and research? You mentioned the advice taker.
Right, this is a really influential early idea. It was a hypothetical program he proposed in a 1959 paper called Programs with Common Sense.
Programs with common sense. I like that.
Me too. And the key idea, probably the first proposal of its kind, was to use formal logic to represent information inside the computer. Not just logic as a subject for the computer to analyze, but as the way the computer stores and reasons with knowledge.
So teaching the computer facts using logic.
Exactly. And the big advantage he saw was that you could improve the program just by telling it things, adding new facts, new rules in a logical language.
Instead of reprogramming it from scratch each time.
Precisely. You just make statements to it about its world and what you want it to do.
Yeah.
He defined common sense for a program as its ability to automatically figure out the immediate consequences of what it's told based on what it already knows.
That sounds much more flexible.
Way more modular, more reusable than just writing specific code for every situation. Using declarative sentences, facts, was the key.
And this focus on logic and common sense stayed with him.
Oh, absolutely. It was a central theme throughout his career. He wrote a key paper in 1990 called Artificial Intelligence, Logic and Formalizing Common Sense. He argued that understanding the common sense world through logic was a vital approach to AI, different from studying human psychology or brains, but complementary.
Why did he think common sense was so fundamental?
He had a few reasons. One, scientific knowledge is specialized, right? You need common sense to actually apply it in the real messy world.
Makes sense.
Two, for real-world problems, you often don't know all the relevant facts or potential problems in advance. Common sense reasoning helps you navigate that uncertainty.
Okay.
And three, Even how scientists talk about their theories informally relies on a shared background of common sense.
He also talked about epistemological adequacy, didn't he? What's that about?
Yeah, that was from a '69 paper with Patrick Hayes. It means a knowledge representation system, a formalism, has to be able to represent the information that's actually available to the system in the real world.
Not just some perfect, complete picture.
Exactly. His example was like a store clerk. You don't need a full psychological profile to interact with them. You just need to know the typical facts about how clerks behave, they take money, give change, etc. AI needs to work with that kind of partial, practical knowledge.
So, dealing with the real world's incompleteness, did he respond to critics who said computers couldn't handle ambiguity, that sort of thing? Like Hubert Dreyfus?
He did engage with those critiques. McCarthy believed that by formalizing something called non-monotonic reasoning, AI could handle ambiguity. It could make default assumptions and then revise them if contradictions arose.
Non-monotonic reasoning. You mentioned that. Can you break that down a bit?
Sure, so standard logic is monotonic. If you prove something is true, adding more information never makes it false. It stays true.
Once true, always true.
Right. But human common sense doesn't work like that. We jump to conclusions based on typical situations, but we retract those conclusions if we get new information.
Okay, like you assume a bird can fly.
Perfect example. You assume birds fly. Someone gives you a bird cage, you assume it needs a top. Then they tell you the bird is a penguin.
Ah, right. Penguins don't fly, so you retract the needs a top conclusion.
Exactly. That's non-monotonic reasoning. McCarthy developed a formal method for this called circumscription between the late '70s and mid-'80s. It was a way to mathematically capture this idea of making plausible assumptions and retracting them when necessary, a big step for formalizing common sense.
Fascinating. He also worked on formalizing context. That sounds crucial, but tricky.
Very tricky, very crucial. His idea was to use formulas like holds, A, P, C, meaning proposition P is true in context C. He thought about relationships between contexts, like some being more general than others.
How would that help an AI?
Well, think about understanding language, like he's in the car. The meaning totally depends on the context, who's he, which car, when. But McCarthy saw the main AI use as reasoning about actions and goals. The context determines what actions are possible or what their effects will be.
Right, context changes everything. Okay, one more specific idea, his claim that even simple things like thermostats have beliefs. That caused a stir, didn't it?
It sure did. That was from a 1979 paper ascribing mental qualities to machines, saying a thermostat believes it's too cold. Well, it's a functional definition, right? It acts as if it has that belief to achieve its goal.
But it sounds provocative.
Highly provocative. It famously led to philosopher John Searle's Chinese room argument, which questions whether machines can genuinely understand or just simulate understanding. McCarthy's point was more about finding a useful, formal definition of belief applicable across different systems.
So beyond these specific ideas, what about his impact on the institutions of AI?
Huge. He was at Princeton, Stanford, and IT top places. He spent most of his career as a professor at Stanford until 2000. And crucially, he helped launch one of the very first major university AI labs at Stanford back in 1965.
Creating a hub for research.
A hugely influential one. Stanford's AI lab became a powerhouse.
And wasn't he also involved in early computing infrastructure ideas like time sharing?
Yes, a massive advocate for it. He was key in developing early time-sharing systems, CTSS, BBN, Dartmouth time sharing. This allowed many people to use one big computer simultaneously. Think about how that changes access and collaboration.
Completely transformative.
And even more visionary, back in 1961, he suggested utility computing, the idea that computing power could be sold like a utility, like electricity.
That sounds exactly like cloud computing.
Pretty much.
Yeah.
Decades ahead of its time. He also influenced the design of AlGOL, another important early language, pushing for recursion and conditionals there too.
Wow. So, summing up, John McCarthy's influence is just enormous. He literally gave AI its name.
Coined the term, yeah.
He built Lisp, the language that powered so much early AI.
The workhorse language for decades.
And he laid down these fundamental ideas about logic, common sense, context, non-monotonic reasoning, concepts we're still grappling with today.
Absolutely. His vision shaped the field in profound ways. And his work was recognized, of course. He received the Turing Award in 1971. That's like the Nobel Prize for Computing.
It's a huge honor.
And the U.S. National Medal of Science in 1990, the Kyoto Prize in '88, These really underscore his monumental contributions.
A true giant. So, to wrap up this deep dive, let's leave you, our listener, with a thought inspired by McCarthy. He believed quite strongly that human-level AI was achievable, maybe even with computers from decades ago, if we just knew how to program the intelligence itself.
The hardware wasn't the ultimate barrier in his view. It was the understanding, the algorithms.
So the question for you is, as AI surges forward today with vastly more powerful hardware, what fundamental aspects of intelligence, of common sense, of reasoning do you think we still fundamentally lack the understanding to program effectively? And what might that mean for the future path of AI?
Thanks for listening. If you enjoyed this episode, please like, subscribe, and share. It really helps us grow. See you next time.